Welcome to the pre-recording of lecture 8 of MCS 260. So this is the second part of the fourth session in the 8-week summer course. In this lecture, the if, else, elif statements are introduced. Before that, we need to know about the Boolean algebra, and then also about the type bool that is available in Python. Boolean algebra. So we are going to build conditional statements. So we are going to compute or evaluate expressions that return true or false. True corresponds to the value 1, false to the value 0. So true and false are other words for the bits. We can combine them, and the outcome of the operators and, or, and not, they are described in truth tables. I did not include the truth table for not because it's negating the true or false. True becomes false, false becomes true. If you look at the truth table for the and, you can read this also if you look at the first columns, and if you see the values 0 for false and 1 for true, then you see 0, 0, 0, 1, 1, 0, 1, 1. So that view of the AND as the binary addition, so the first two columns essentially list the numbers 0, 1, 2, and 3 in binary. That view may come handy when we want to compute truth table. So in any expression you list all the combinations. So if you have two variables in the logical expression, you have 4 rows. If you have 3 variables, you have 8 rows, because 8 is 2 to the power 3. So the OR is giving you, so you only get a true when both arguments are true. You only get a false with an OR operation is if both operands are false. Okay, the order of operations matters. So typically we don't place brackets around the not because the not is always first evaluated before the and then finally the or. If you know these rules, then you do not need to put the brackets, but in general, for readability, it's good to actually place the brackets. There are logical laws that are very useful to simplify expressions, especially if you are building electronic circuits, but also as a programmer. Simple programmers are easier to evaluate for correctness. It's also good, and I should have mentioned this with the truth tables, it's also good if you are looking at conditional expressions in your program that you go through all the possible outcomes. Mistakes often occur in programs when the programmer did not foresee a certain state. So we will see the if and the else statement. It's often good to think about if there is an if, then what you need to do, but what if the if does not hold? So sometimes nothing needs to be done and then that is fine, but sometimes it's also very good to actually cover all the cases. So the Morgan's law simplify expressions, and it's an exercise to actually write down the truth table for these expressions. So we have the truth table for x and y. If you make the truth table, you have additional columns for the left expression. So you have the not x and the not y column. Then you have the or that combines the not x and the not y. And then you have the not of that result. So in proving the laws with truth tables, so 4 rows, um, 2 columns for x and y, 2 extra columns for not x, not y, so we are 4 columns, a 5th column for the or, and then a 6th column for the not. And then you should see that what you get out of this is x and y. So this is a formal computation of a verification of a statement. So intuitively, and perhaps I should have started with this, so you see an example of if you are not being alive or you're not being well, then actually if you negate that or, it means that you're being alive and you're being well. So for the example, I constructed from the right to the left. Going to school or going to work means that it's the negation of not going to school or not going to work. So again, if you want to make very complicated phrases, you can use the Morgan's laws used from right to left, but typically in programs we want to simplify them. Simplify conditional statements. Flowcharts are pictures of algorithms, and they have at their center the diamond for the test. So here is an example. Conditional statements are often embedded in functions, and also they are embedded often in data structures. So the first part of the session was on dictionaries. Here we have the mathematical expression of a condition statement expressed by a mathematical function that is going to tell you to flip the sign of a number if the number is negative. So you see here how in mathematical notation we have an if statement. Also, you could see from previous mentioning kind of the rule-based viewing of coding. Okay, so translating, so we are programmers, we are thinking about formally describing algorithms. Pseudocode allows us to formally describe an algorithm. So formal means here unambiguous. So the unambiguity is one of the key ingredients in the definition of an algorithm. Pseudocode is not really real code. So here in the example, so this is the printing of the absolute value of a number. You ask the user for a number, or you prompt for a number. If and what follows the if is the test. If we have a negative number, and if we have a negative number is perfectly fine to write this in a condition in pseudocode, then you print a negative sign and then you print the number. In the other case, you print the number. So you see printing the number is done twice, and there's always the temptation to simplify this. So you could think of moving the printing the number as the last statement anyway, unconditionally what you have to be doing. Here is the flowchart description. Central stands the diamond for the condition. So if we have a negative number, then we print negative x. Otherwise, if the test returns false, we print the number. So this flowchart is probably a little bit neater than the pseudocode. And you can see that it's already a little bit forcing you to be a little bit more formal because what goes into the boxes is limited, although you can, of course, make your boxes as large as you like. So we've seen this with one of the tools in Jupyter Lab, the diagram. Okay, so let's go now to Python. So I have scripts prepared and I have a Jupyter notebook open. So let me summarize the essentials, what you need to know from this lecture. So this is kind of the key slide for a Python programmer. So the Boolean or the type bool is Boolean for the person. Boolean, Boole, George Boole, but then written with an E at the end. The logician, and also with roots in computer science, if you like. So it's an elementary data type and it actually could have been considered as the first data type, corresponding to the bits, the 0 and the 1, false and true. Python uses the equal sign as an assignment. That's a little bit unfortunate. You must use the double assignment, the double equal sign, not the double assignment. So the double equal, two equal signs if you want to compare. Um, and that could be often a bug. So you may want to mean a comparison, but what you're actually executing is an assignment. Notationally, that is a little bit unfortunate. So there is the comparison of values, and there is the comparison of objects. For composite objects, this is different. So you can have two lists that hold the same values and are therefore considered equal, but are still separate objects. I will give an illustration of this. Python is a very powerful language that comes with data structures included. So one of the courses in our curriculum following is a data structures course. Data structures are critical when you think about programming. Programs equal data structures plus algorithms is the title of a very influential book. So, as I will try to illustrate, it sounds a little bit sophistic. You can, if you don't have an if-else statement, you can already write general programs. Remember the definition, what an algorithm does. It transforms, it describes, and it transforms information. So if you use a dictionary for an if-else statement, you have to provide two keys, a true and a false, and the values are storing the code. What happens in the if case is the value corresponding to the true key, and in the else case you have the code that stores what happens in the false statement. So I will illustrate how you can actually write programs that are more oriented towards the data structures. Because dictionaries are very well provided in Python, it looks far-fetched for regular programmers from previous generations of programming languages, but in Python it is possible. Okay, so now the if else. So this is a control structure. So when we program, we use control structures to branch in the code. So we have code, and sometimes based on the input data, we execute one branch or another branch. So here is the syntax. I'm using a little bit the Backus-Naur form. So what is between the less than right, the less than and the greater than symbols should be interpreted as first a condition, and then after the condition you have the statements. Python doesn't have a then keyword, but it uses the colon. Sometimes when I come from a language like C++, I forget the colon. So in Python, there is the colon, which you should not forget, which resembles the then. And Python is blocked-oriented language, so it's statements in plural. So it could be an entire code block, but all the statements that should be executed after when the condition is true, so all statements that belong together must be preceded with the right number of spaces. I'm a little bit adverse to tabs. I don't like tabs, so I'm using 4 spaces each time. Here you see an example. Syntactically, both statements are correct, and also semantically they are correct. So this is an example of a logical error. So both statements will be executed exactly. So if you want to print out, so we had the example for the absolute value where we place a negative, where we flip the negative for a plus. Suppose that when we print numbers, we not only want to see the minus in case of negative, but we always want to see the sign. Then with an if statement, we could do it in 2 ways, but actually only the second way works correctly. If you use the first code, so perhaps let me indicate this. So in the first code, I have used the same number of spaces for the 2 statements. That means that both statements are considered as belonging to the same block, and they will be executed only if the number is positive. So this code will print nothing. It will print nothing if the number is negative. So this statement here at the right is outside. It is at the same level as the if, and it will be executed no matter what the condition returns. If it's true or false, if the number is positive or negative, it will print the X. Now, be mindful, the print actually uses a new line. You can suppress the end of line symbol. So I should have indicated this. So this code, you can suppress the end of line with, if you look at the help of print, you can do that. All right. If you have an if, then if you think about the correctness of programs, you could think always about is there an else statement? So we had the absolute value of a number, and here you see the code that corresponds to the mathematical definition and the flowchart. So this is one of the simplest examples that I could think about. But again, the same admonishments hold. Do not forget the colon. So I said that the colon was operating as a then, but actually that's not really true, because after the else you have to put a colon there as well. So all the statements that belong to each other, that have to be executed at this when the condition is true or the condition is false, they have to be preceded by the same number of spaces. Okay, here you see more complicated. um, diagram. A grade scale. And I must confess that here, if you were to do this with truth table, you can with a dictionary, you can still do this, but it will involve quite some nesting, and it you can do it. So based on the test, you first test 90 or higher, and if that is false, then you would go to the other case, and that would be a dictionary within the dictionary. But you get from the flow chart the logic, and you can read the algorithm that assigns a letter grade based on the input number n. So there are 4 tests. There are 4 statements that are happening in case the test evaluates to true. And then there is the final statement, the default, if you like, the grade equals F. Now, the assignment of the grade is actually assigning a letter grade. So this is not Python, so it's pseudocode inside the um, execution statements, but you get the algorithm. Okay, so you can implement this with an if else statement. This goes with nesting. But if you have so many cases, then the code will shift gradually towards the right and towards the end of your page. So here you have the 4 spaces that are default, that are making it kind of obnoxious if you have too many conditions. You can avoid this with the elif. So elif is a contraction of else if. So if you do not know about the elif, that's fine, but then you have to use the else if. And then between the else and the if, there is no colon in that statement. The grade scale is optimistic, so we are assuming that many people will actually get an A in this class. So that's the condition that we first evaluate. So if you want to optimize for execution efficiency, you first put the conditions that are going to evaluate it most often to true. As a programmer, it's often good to think about the cases that are easiest to handle. So it's so much easier for me as an instructor to give an A than it is to fail anybody. So I was perhaps also mindful to that. But if there is only, or if there's only one statement in condition one, as a programmer, and if that is a clear-cut case, as a programmer, you put the easiest statements often first. So in this course, we are mainly concerned with correctness. Okay. So I mentioned the proving of De Morgan's laws. So in a way, this is a mathematical course. So you can formally prove these laws just by creating a truth table with 4 rows and at least 6 columns for all the sub-expressions in the statement in the left-hand side of the Morgan's law. So this is a very good exercise. So the other 3 exercises we will be able to do when we get through the second part of this lecture. So in my Jupyter Lab environment, I now switch to the other tab for the demonstration, the experimentation with the Boolean type. So You get the Boolean type automatically if you start evaluating comparison operations. So 1 is obviously less than 7. Um, if you want the less than or equal, you have the less than and then the equal sign, as here demonstrated with the greater or equal. Um, be mindful of the equality and the inequality. So you have the exclamation point and then the equal. You can also do this with the not operator. If you forgot this exclamation points equal, you can do not 1 equal 7. That will work as well. We introduced format strings. Format strings return the string representation, so it's an alternative to the str method that is defined also for any object, also for variables of the type bool. You can print to the integer value by the fixed floating point format and then a dot. But after the dot, you say that I don't want any numbers after the dot. Then it will also not display the dot anymore. So you can see that corresponding to true, we have 1, the string 1 here, so you have to apply the eval to get the integer 1. And false correspond to the integer 0. So we are not so much concerned with efficiency in this course, but you could think that the true and the false then might be stored in much more compact form than say an integer. But in Python, integers they are actually at some point becoming arbitrarily long. Okay, so with and ors, we make logical expressions. So as you may use in conditions in the if. So we have variables. So here you see the assignment of 3 to the variable x. And we can check that x belongs to the range 1 and 10. Is 1 and 9, so it's a single digit. So if you want to test whether your integer number can be represented by 1 decimal, then this would be the test. You can also check if the number is negative or less than 5. That will also evaluate the truth. And if you do not like the greater than equal combination, well, you can test the number is not negative. I have included brackets. They're not strictly necessary. You can actually remove them in all circumstances, in all the examples here, but I prefer them because of the readability. So the brackets are actually telling you how to evaluate, how the evaluations are happening. The brackets are necessary if they were necessary in the De Morgan's law, so I probably should have pointed that out too. You can so the homework answers need to be provided in a Jupyter notebook. So you could first do the exercise on paper and pen and then type things up. But with the Morgan's laws, you can actually evaluate the law for the various values that you have. And in this way, compute all the columns in the truth tables. So these are proofs in the mathematical sense, but they're also computational. So they are computing things. The last two sections in this notebook are a little bit more sophisticated. So perhaps too uh, too far-fetched for this first encounter. But we have seen the references with lists. So lists are extremely versatile and very useful data structures in Python. They correspond to loops. So dictionaries corresponds to conditional expressions. We have actually used for loops already when making lists. So we have two lists, L and K. They are both the same, as you can see, but there are different objects. So from a purely mathematical perspective, they refer to the same lists, but as objects, they are, and also from a computer science perspective, in main memory, they reside into different spots. So that's why the is gives a false. So you can have both is and equal giving true if here in this case we have the same objects. Okay, then I mentioned that dictionaries can do the same as if else statement. So suppose that you want to congratulate somebody when the score is more than 80, then that is the message that will be printed if the test evaluates to true. Otherwise, you kind of invite to try again. So suppose that 80 is the threshold at which the pass-fail would happen. Then you can encode the messages, or in general also encode the statements. So with the eval, we would evaluate the expression. So we can encode an arithmetical expression inside a string. The two keys for the two cases are true and false. And you see how this message can be computed by giving a conditional expression that will be evaluated to the key true or false, and that will therefore then compute the corresponding message. So this is how you can define the conditional execution of statements by a data structure. Okay, very good. I'm at half an hour here, and that is excellent because I want to go through the writing of programs. So I have another tab prepared. So I have 3 Python scripts prepared. So here is the alternative, and programmers might say a much more conventional and less far-fetched coding of the message of printing of the message. So we have a number. So first of all, this is a full program with a documentation string. So a documentation string is not necessary for a program, but very, very strongly recommended. So it's kind of introducing what the program is doing. Okay, we are going to congratulate user if the user types in any number larger than 80. The number first occurs to us as a string. So in data, that is everything that the user enters. So if the user enters a character, the program should crash on the statement where we convert the data into an integer. But assuming here the user is on their best behavior, so we do not assume type errors. So we will print the message in the else, in the if case, we will print the congratulations, and then otherwise we will print the sorry message. Okay, so this is typeset in a .py file, very important. It's also typeset with the editor that is provided by the Jupyter Lab environment. So you can see with the coloring is that this editor understands Python. You see the color coding for the strings, the color coding for the values and the statements. Now, this is starting to program. I give you a complete program, so I will execute it now in its entirety. So I want to see congratulations, so I will print 90. If I run this again, very useful, the arrow up key. If I type 7, then there is the sorry message. So sometimes it's not really that pedagogically justified that I'm printing this with um, that I'm showing the entire code first. Um, and perhaps let me go back to the other example that I want to show now, the grade curve. So here you see the grade scale. Um, the first statement is already here, so I am making another, I'm going to the Launcher tab. Starting from scratch, I will click on the Python file. So there are many choices here. If you want to start editing, you start with the uh, Python editor, and you start with a simple documentation string. So we will implement, so prompting, we prompt the user for a number and write and print the corresponding letter grade. It's good practice to actually save this and already give this another name. So you will have untitled all the time, and that's not so good. So it's the curve for the grade that is shown. So I just will call it curve. Normally not much will go wrong here, so I will continue typing. I will, sorry, remember the previous statement. So I have data, the input, give a number. So I will prompt the user for a number. And I want to execute this. I will just print it. So remember to save this. So click on Save Python file. And now go to your PowerShell and do Python curve. Give a number 90, it prints 90. It has no error. Okay, so let me continue. So I have to compare data. So this is a statement that I'm not going to use. So if something is working, you can comment it out. So you can go back to this. The triple quotes are also very useful to document out. So triple quotes are documentation strings or any strings of multiple lines. Triple quotes are also very useful to tell the Python interpreter, please ignore anything that is between the triple quotes. So if the number is larger than 90, so let me go back to the flowchart. Here it is. If the number is larger than 90, then I will have the grade equals to A. But notice the n is actually here an integer number. So it is pseudocode, but not entirely complete. Because here in the pseudocode, when it's meant for human readers, we don't really distinguish between the number and the string representation. In a computer, we have to make this distinction. So my number is an integer. So I'm using integer arithmetic. You can say, well, this is probably not too good, and then I agree with you. So, what is the rounding? Perhaps I should have it as a float. So I will compare against float. So otherwise, I may round down. Um, um, if the number is larger than equals to 90, then the grade, the letter grade, so the grade will be an A. Um, so you see the editor is helping me, but actually I want to print the grade. So what I'm trying to get at here is that if you are looking at this entire flowchart, there are many, many tests there, and you may want to do them all at once. So typing everything in, that is in general not good practice. You have to save the save early and often, and also execute early and often. So arrow up, I'm executing it again, and you see that I get a 90. So what happens actually if you have 89 plus 5? Then actually it gives me an error because 89.5 as a float is not larger, and you can see the name error. There was no assignment that was being done to grade. So this is a runtime error. The error is actually a logical error. I have not covered the case when the grade is not defined. Let me do this. So the default case is the failing. So let me now do something very realistic. So, and again, I kind of, so I'm saving this again. So now my program will not crash. So again, the project is due at soon. If you are in a hurry, try to write a program that works and that covers part of the basis. So this is the illustration of the basic if else. So again, if you test this, test all cases. If you change your program, test the cases that worked and also test the cases that didn't work. So here you see that you get an F if you have 89.5. Not very good, so there is typically rounding that will be applied, so that should be an A, but also still very terrible, because what about the other letter grades? Okay, so there are cases in between. So there is the elif, and you can see when something. So I'm going to do this. I practiced this, or actually we just saw this, so it's still fresh in memory. Um, but notice if you would forget the semicolon, then actually it still shows green. So my editor is actually not really helping. So let me save this, saving the Python file, and then running it again. So there is actually an invalid syntax. So the elif is not correct. What happened? So let me go to the slides. So this is the elif, and I forgot a condition. Syntax error again. So the condition is that the number is larger than 80. Save and execute. So again, all the cases. So now you see that, perhaps I should have explained this. This was a good error that I made. When you execute a program, the Python interpreter translates statement one after the time except when it doesn't. So you see it looked ahead and it didn't prompt for a grade. It already gave the error at the incorrect second statement, the if elif. So it looked ahead and then you actually got a parsing error, a syntax error. All right, this case still works, and now 89.5 will result in a B grade. Anything less than that, so the case 78 will result in an F. Very bad, so let me add for completeness this case. So we have the elif. If you have more than 70, then the grade is C. And there is actually also, I'm feeling now a little bit in a rush because I want to illustrate something else. And I'm feeling also more confident. So the other case is the D case where there is the 60. Not forgetting the columns. All right, so this is a complete illustration of an if-else. Don't forget to save before you go to the PowerShell. And now let me now immediately print out 78. Also check the 98, for example. Check the 88 and check the 66, which gives you a D. And for all other numbers, say 7, we get an F. All right, in a way, this is the essence of the lecture. The last case that I want to show is a nested else if. So here is a simple dialogue. Are you happy? If the answer is yes, if the then keep up the good work, keep on doing what you're doing. Otherwise, perhaps you are bored. Well, don't worry, this meeting is soon over. And it's not Friday, I probably should have said, but this is a sunny day. But let me fix this. I'm sorry to hear this. Sorry about this. I hope this is not the case that you are happy. So let me change this program and save this. So the point is that this is a good case analysis. So you have two states, so two prompts. Yes, two times the answer. And actually you have to check all the cases. And there are three cases here. So if you're happy, then there is no follow-up question. I mentioned that the no follow-up, so in a little bit pedantic case, so it's the easy case. So, and for simple coding, I could have moved this single statement to the yes case. But I wanted to indicate the indentations. So let me run this. So this is the follow-up code. So I'm not happy and I'm a little bit bored. Don't worry, the class is soon over. If I'm happy, no problem. And then I have the case where I'm not happy and I'm not bored either. But there is something else that's bothering, like the room getting too hot without air conditioner. Okay, I'm running almost overtime, so let me go now to the slides back again. So the purpose is that you can go to the exercises, draw the flowchart either by hand or practice the diagram tool in Jupyter Lab. There are numbers, integer numbers that are prime or not. You can write a program for the first primes. So the first primes are 2, 3, and 5. Um, you can, so I suggested the first exercise that you could do this essentially on pen and paper, but you can also do this with a Jupyter notebook. And you can set up the Python dictionary for the truth table, which will be a nested dictionary. Later, we will see how we can actually compute the truth tables, have programs that generate these truth tables. Okay, so we have defined in this session the dictionaries, and in this lecture in particular, the if-else statement as the control structures. This is almost the essence of programming in the small.